Welcome to this lecture comparing NPUs, GPUs, and CPUs for AI workloads. In this talk, we'll explore performance, efficiency, and where each processor shines. The title slide previews charts and a system diagram, and over the next slides I'll walk you through architectural differences, benchmark results, power implications, and practical guidance for choosing the right processor. This slide highlights architectural specialization. CPUs excel at serial control flow with complex cores and branch prediction. GPUs deliver massive parallel throughput with tiled processing and high bandwidth memory, while NPUs optimize neural efficiency with MAC arrays and minimal data movement. I'll explain how these design choices trade latency, throughput, and power to suit different AI tasks and deployment constraints. Here we compare Llama 3. 1.8B latency across platforms, showing dual GPU at about 5.27 seconds, a single NPU at 4.84 seconds, and a multi-NPU configuration down to roughly 2 seconds, à 62% réduction versus dual GPU. The right-hand diagrams show why. GPUs face queuing delays from shared memory and schedulers, while NPUs use fixed-function pipelines and on-chip SRAM to slash queuing and improve end-to-end latency. This slide presents Batch 1 inference performance, where NPU 2 achieves about 3.67 images per second versus GPU 2's 3.22, a roughly 14% NPU advantage for edge scenarios. The workflow diagram explains the win. GPUs suffer warp underutilization and DRAM spills at small batch sizes, whereas NPUs sustain higher utilization through specialized data flows, illustrating that targeted specialization can outperform brute force parallelism for Batch 1 workloads. Power and efficiency comparison shows big differences. GPU 2 peaks near 314 watts for SDXL Turbo, while NPU 2 peaks around 94 watts, roughly a 70% reduction, enabling significant power savings for generative models. The right chart shows power scaling with model size, implying lower cooling and infrastructure costs, longer battery life for mobile devices, and overall cheaper, more efficient systems when NPUs are used appropriately. NPU efficiency scales favorably with model size, offering about 1.3 to 1.9 times better tokens per watt, or FPS per watt, compared to a GPU baseline, and experimental edge NPUs, reaching roughly 38.6 TOPS per watt on ResNet 5.0. The plotted curve shows the efficiency gap widening as models grow, reinforcing the idea that NPUs become increasingly attractive and energy efficient for large parameter models. GPUs remain the preferred choice for high performance, versatile workloads like training huge models, massive batch cloud inference, real-time graphics rendering, and mixed AI plus graphics pipelines. Decision thresholds shown here include batch sizes above about 32, memory footprints over 20 gigabytes, or requirements for double precision math, all of which favor GPU selection when flexibility and raw throughput matter most. This slide frames the CPU as the orchestrator. CPUs handle pre-processing, control logic, real-time OS tasks and legacy code, while feeding queues and offloading work to accelerators. GPUs serve as parallel AI and graphics accelerators for high-throughput matrix math, and NPUs act as dedicated AI accelerators focused on optimized inference paths and low-power, high-efficiency matrix operations in production pipelines. Heterogeneous compute integration is illustrated with Intel Lunar Lake, Apple M4, and Qualcomm Orion, each combining NPU tiles, CPU cores, and GPU slices around unified memory and on-die interconnects. The diagrams contrast traditional high PCIe latency systems with integrated designs that cut latency, use shared memory access, and apply dynamic power gating to achieve adaptive efficiency across workloads and devices. Software ecosystem maturity is critical. Cross-platform frameworks like ONNX Runtime, OpenVINO, and VLM increasingly expose NPU backends, while compilers such as TVM auto-partition model graphs across CPU, GPU, and NPU for optimal execution. A maturity timeline shows frameworks support trailing hardware by about 12 to 18 months, so early adopters can gain advantage, but should watch evolving toolchains to reduce vendor lock-in risks. The processor selection guide maps application constraints, power budget, batch size, model memory, and software heritage to optimal choices. NPUs are ideal for low-power, sub-100 watt edge boxes that prioritize latency and efficiency. GPUs excel for cloud-scale training and large batch inference, and CPUs remain necessary for control plane tasks, compatibility, and legacy systems that need general-purpose support. Finally, workload profiling and optimization convert theoretical NPU advantages into real savings by measuring end-to-end latency, tracking power at the wall, and accounting for total cost of ownership, including cooling. Practical strategies include adopting quantization early, leveraging compiler stacks to design zero-copy data pipelines, and exploiting shared memory for speed, all aimed at ensuring measurable reductions in cost and power in production.